Good morning, all. In this lecture, the topic is half wave and full wave control rectifier. In the previous lectures, we have already discussed about that what is your control rectifier and uncontrolled rectifier, and what are the different types of control rectifier, and what kind of power electronics element or device we use to making the uncontrolled rectifier, and what kind of power electronics elements we are using to making the control rectifier. So these this is the topic of half wave and full wave control rectifier. Now, uh, course objective is of this lecture is to introduce students to the basic theory of power semiconductor devices and passive components and their practical applications in power electronics. To familiarize students to the principle of operation, design and synthesis of different power conversion circuits and their applications, and to provide strong foundation for further study of power electronic circuits and systems. Now, these are the course outcome. After this lecture, I'm expecting from student that student will be able to understand the half wave control rectifier and full wave control rectifier and their working and analysis of their waveforms or their output waveforms. So I'm expecting from student that student will be able to understand each and everything. Okay, so we will discuss now how wave control rectifier and full wave control rectifier and what are the advantages and disadvantages. So different types of single phase control rectifier is half wave control rectifier, full wave control rectifier using a center tapped transformer, full wave bridge circuit, and a semi converter and full converter. So first, these are the single phase means you can divide converters into two parts. One is your single phase converter, and another one is your three phase converter. In single phase converter, you can see or check that the no half wave, in half wave, single phase half wave control rectifier or maybe a full wave control rectifier, you are using only one phase and one neutral wire. Okay? And the components we will use to making the half wave rectifier and full wave rectifier in single phase, the component required which is less than the component which is required in your three phase controlled rectifier, right? So these are the different types of your control rectifier. With control rectifier, full wave control rectifier, using a center tapped transformer, full wave bridge circuit, semi converter, and full converter. Now, different types of three phase control rectifier: half wave control rectifier, full wave control rectifier, semi converter, and full converter. Okay. So in semiconductor, we can call it half controlled bridge converter, or you can say full converter means fully controlled bridge converter. So, what are the basic principle of phase controlled rectifier operation? If you are using the term controlled with rectifier, it means you are not using diode. I have already previously discussed in our last lectures that if you are using controlling word in power electronics, that you are using something controlled device which can be controlled by its gate terminal or by its voltage or current. Okay, so if we talk about principle of phase control rectifier operation, that we are using SCR, GTO, or any other components. So basically, in generally we use SCR in phase controlled rectifier. So first we will discuss about single phase half wave thyristor converter registered load. So what is actually what is the uh, what is your single phase half wave thyristor control converter? So you can see that you can see that this is your half wave thyristor converter, in which you can see that we are using only one SCR. There is a transformer it has two windings. One is your primary winding and second is your secondary winding. In primary winding, the voltage is your VP, and in secondary winding, the voltage is your VS. So this is your primary and secondary winding, and you can see that in primary, the thyristor is connected to the secondary winding of the transformer, and there is a one load we are connecting through resistance. So this is all about your single phase half wave thyristor controlled converter. Now, this is your supply voltage and you are getting output voltage. So you can see that from the waveform, the input voltage is your AC voltage. So the positive half cycle is from 0 to 5 and the input voltage is your V1 and VM is your maximum voltage of your input voltage. So you can write it as Vs. Vs is your input voltage, Vm is your maximum voltage, and V1 is the voltage where at point at this V1 voltage you are giving the SCR, and we have already discussed about the SCR and what is SCR and how can it control your output voltage and what are the different terminals it has. It has three terminals. One is your anode, cathode, and gate. So through the gate terminal, you can easily control the output voltage of the SCR. So what do you understand by output voltage of the SCR? Output voltage of the SCR means that SCR is not giving any kind of output voltage until and unless you connect it with with supply. Okay, when you connect SCR with the input supply, then you will get the output voltage and you can control it by you controlling your gate terminal, right? So in supply voltage, you can see that V1 and V1 is your supply voltage and V1 is your input voltage. So at terminal alpha, you can control the output voltage. So what we are doing, you can see from the diagram that this is your input voltage, positive half cycle 0 to 5. If you are using one SCR, because SCR is also a unidirectional device, it can the current can be flow into the SCR from cathode to anode. The flowing of current in SCR is anode to cathode. Okay, so for positive half cycle, only one SCR will work, and you can see at this point alpha. Okay, alpha is your triggering angle or firing angle. Basically, this is called firing angle in SCR. So this may be it is less than 90 degree. You can easily see from the diagram that it is less than 90 degree. So it may be or 10, 20, 30, 40, 50, 60 or 70 or 80, 85, 82, any angle which you want, and it depends that how much voltage you require in the output. So at alpha you will trigger the SCR before triggering before this angle. If you are not giving any kind of firing or any kind of pulse on this on its gate terminal, the thyristor will not start to conduct. So the point is at this point alpha, the SCR will start to conduct. Okay, so you are getting output from alpha to pi. You are not getting this much of output. Okay, so by varying this firing angle, you can easily control the output voltage. Now the third waveform is your output current. So you can see from the diagram that the output current means that the current which is you are getting in the output. So it will depend upon that how long your SCR is conducting. Okay. So in this waveform we can see that when thyristor is triggered at point alpha, then it will conduct from alpha to pi. It will not conduct before alpha and it will not conduct at pi. Why it is happening? That it is why it is not conducting after pi, because the first thing is that the load is resistive, and in the resistive load the voltage waveform and the current waveform will be similar. And the second thing is that after pi, the negative cycle is appearing or negative voltage is appearing across the SCR. So if negative voltage is appearing across the SCR SCR, uh, come into the forward blocking mode. Okay. So when it comes into the forward blocking mode, there is no conduction, there is no current flow through the SCR. This is the ideal condition. Actually, for some time it conducts or it takes time to turn off. But in present scenario, there are many power electronic devices or power electronic components available which has very fast switching devices. So you can easily control your output voltage by fast switching of these devices. So this is all about your, wave rectifier and full wave rectifier. So this is your supply voltage, and if you talk about thyristor voltage, because 0 to alpha, thyristor was not conducting. If thyristor was not conducting, what does it mean? That the voltage will appear across the, there will be some voltage which will appear across the SCR. So this voltage is your VT1. This is called your thyristor voltage. Now, these are some equations by which you can easily uh, understand the working principle of phase control rectifier. So Vs is equal to Vm sine omega t. This is your input AC supply voltage. Vm is equal to maximum value of input AC supply voltage. Vs is equal to Vm upon root 2 RMS value of input AC voltage. V naught is equal to VL output voltage across the load. So when the thyristor is triggered at omega t is equal to alpha, V naught is equal to VL is equal to Vm sine omega t. So omega t is equal to alpha to pi. Okay. So I naught is equal to IL, IL is equal to V naught upon R, and omega t is equal to alpha to pi. So I naught is equal to IL, Vm sine omega t upon R, which is equal to Im sine omega t alpha to pi. So where Im is equal to Vm upon R, maximum value of load current. So this is all about your, how they control rectifier. Now we will discuss about the next topic, which is
converter fall generally into four categories. One is your AC to DC converter, that is your controlled rectifier. Okay, so power semiconductor devices, or you can say power electronic devices, uh, can be used to convert AC to DC, DC to DC, AC to AC, and DC to AC. So the design of power electronic converter circuit requires design the power and control circuits. The voltage and current harmonics that are generated by the power converters can be reduced or minimized with a proper choice of the control strategy. Power electronics application. So what are the power electronics applications? Power electronics defines as the application of solid state electronics for the control and conversion of electric power. Power electronics have already found an important place in modern technology and are now used in a great variety of high power products, including heat controls, light controls, electric motor control, power supplies, vehicle propulsion system, and high voltage direct current system. So we can see that power electronics has huge applications in all field almost. Okay, so it is very important and very interesting subject, right? So power electronics switches devices. One is your actually these are the different power electronic switches. By using of these switches or these devices, we can control our power. I have already explained what is power and how it controls by using power electronic devices. So these are the different switching devices by which you can control the power. One is your uncontrolled turn on and off. This is power diode. Second one is your controlled turn on, uncontrolled turn off. So what is, first we will discuss about power diode. So what is power diode? We already know it is a uh, PN junction. Okay, P type, we take P type and N type, and both combination makes the diode. So what is P type? P type has number of holes and N type has more number of electrons. So power diode is a semiconductor, but it is uncontrolled. You can't control this device. Okay, and how it works? Actually, it has two terminal. P side it has positive, at N side it has negative terminal. When we connect it to the voltage source, positive terminal is connected to positive P junction, and negative terminal is connected to N junction. So what happens? It is in forward bias in this situation. So it will work. If you opposite the terminal, like if you connect positive terminal of diode to the negative terminal of battery and negative terminal of diode to the positive terminal of battery, it won't work. It will be in reverse bias. Okay. So power diode is a uncontrolled device. You can't control the you can't control the power by using this power diode. Okay. Second is your controlled turn on, uncontrolled turn off. This is called thyristor. Okay. So in the thyristor, or you can say it is a silicon controlled rectifier, SCR. So what is SCR basically? What is thyristor? Thyristor is the when you turn on it, it has basically three layer devices. Okay. So what happened? You can control the turn on of this thyristor, but turn off is not in your hand. Okay. Third is your controlled turn on and off characteristic, which is power transistor, BJT, MOSFET, GTO, and IGBT. Okay. So you can control on and off these devices like power transistor, BJT, MOSFET, GTO, IGBT. These are also different type of power electronic devices. We will discuss in detail about these devices later. Next is your continuous gate signal requirement. Uh, okay. So BJT, MOSFET and IGBT required continuous gate signal, or you can say continuous input signal. For example, uh, like SCR, if you take SCR, which is silicon controlled rectifier, in silicon controlled rectifier, first once you have to trigger the SCR, after that it will remain on uh, until and unless you supply your negative pulse, it will turn on. Once you trigger this SCR, it will turn on. But in the case of BJT, MOSFET, IGBT, they continuous required your input signal, right? So next is your bidirectional current capacity triac. Triac is the device which can convert the current, in which current can flow in both direction. Okay, that's why this is called bidirectional current capability device. Third is your unidirectional current capability, like SCR, GTO, BJT, MOSFET, and IGBT. This is your unidirectional. Okay, they will conduct the current only one direction. Okay, they can't conduct the current in opposite direction. Next is here the history. So what is the history of power electronic devices? It is very interesting. Like when it was invented, so first power electronic devices was mercury arc rectifier, vacuum tube rectifier, and thyroton. It was invented in 1900. Invention of thyristor. The thyristor was invented in 1957. And power diode thyristor, it was application of fast switching fully controlled semiconductor devices, which was invented in mid 1970s. And gate turn off thyristor, GTR, power MOSFETs thyristor, microprocessor thyristor, it was invented in 1980. And IGBT, power MOSFET thyristor, this was invented after 1980. Okay, so this is the history of power electronics devices. So this is the block diagram of converter. So by this diagram, we can easily understand the concept of converter, which is used power electronics components. So there are four type of converter. You can see in the first type, AC is converted into DC. In the second type, actually this is the symbol of AC. This is the symbol of DC. This is your yellow box. You can see this is your converter. So you can easily convert AC to DC. Second conversion, you can convert DC to DC by using power electronic devices. Then DC to AC. Then again AC to AC. So by using these power electronic devices, you can easily convert from AC to DC, DC to DC, and DC to AC, and again AC to AC. So this is the block diagram of converter, which always used power electronics devices. Next is your power electronics system. So basically, we have studied, or we have seen different kind of power electronics components, the history of power electronic devices, and basic concept of diode. Okay, so what is power electronic system? Basically, what होता क्या है power electronic system? So generic structure of a power electronic system, you can see in the diagram that this is your power input. Power input is converted into power output by the using of converter. It depends on you. We have already seen the block diagram of converter. By the help of power electronic devices, you can easily convert AC to DC, DC to AC, AC and DC to DC, and again AC to AC. Okay. So generic structure of a power electronic system is given over here. So power input is given. It convert power converter convert power output, whatever output you want, you can easily get by using the power electronic devices. But it required control unit. You can see in the diagram that there is a control unit. So what is control unit? Control unit, feedback. It's a system of feedback. Okay, whatever output you are getting, it again goes into the input. There is a reference. So this output and is compared to the reference. According to that, again you get input. Again, power converter get input, and it gets output. It gives output. So basically, this is the generic structure of power electronic system. So control is invariably required. Power converter along with its uh, controller includes the corresponding measurement and interface circuits is also called power electronic system. Devices available to the circuit design. Basically, these are the devices which can be used to design a power electronic circuit. Okay, so these are the different devices which can be used to create a power electronic circuit. First is your resistor. So what is resistor? What is resistor? Resistor is a device which always opposes the flow of current. Okay, so in power electronic devices, you can use resistance. Next is your capacitor. Capacitor is a energy storage device which store the energy in the form of electrostatic field. Okay. Next is your magnetics. Magnetics, you can say it is electromagnetic. Electromagnetic, not like other magnets. It like a electromagnetic. Like we take two coils. For example, we take two coils. When current is passes through these coils, so it behave like a magnet. Okay, so this is your magnetic. Next is your linear mode, this is your BJT, bipolar junction transistor. Okay, and next is your switched mode. Switched mode means you can see that there is controlling. Controlling means you can see DT1 for the particular time duration we supply the pulses to the device. Okay, when we supply the pulses, then device will turn on, otherwise it will turn off. Okay, sometimes we have already seen that some devices continuously required pulses, and some devices do not require pulses all time. Once it is triggered, it will remain triggered until it off or it is forcefully stopped, right? Next is your devices. Devices which is used for uh, available for the circuit designer. So resistor, capacitor, magnets, and linear mode. Actually, these devices are used for signal processing. Uh, for if you are using power electronic devices for signal processing, so you have to ignore the magnetics. Okay, you can't use magnetics in signal processing. If you are taking power processing, you are using electronic devices for power processing, you can't use resistor and linear mode semiconductor devices. Okay, so these are the different devices we will discuss in detail in other lectures, that how and when which devices must be used to construct a power electronic circuit. Next is importance. So what is the importance of power electronic equipments, or you can say power electronic components? So increasing applications of power electronics equipment in power systems. Availability of high power semiconductor devices, decentralized renewable energy generating sources, increased power transfer with existing transmission system, effective control of power flow needed in a deregulated environment, and norms for power quality. So, what is the use or what is the importance of power electronic devices? For example, we take the example of transmission line system. Suppose, so what happened if you want to improve your electricity quality, or you want to distribute electrical energy on a cheaper cost? So what you have to do? There are two options. One option is, first, totally you can change the system. Okay, the old one must be removed and new one must be added, which is very lengthy and costly procedure. Okay, and the second option is, what you have to do? You can change the existing system by introducing new components, right? So these new components is constructed by power electronic equipments. Okay, so there are n number of PEC devices which is used in transmission or distribution system to improve the power quality and to reduce the cost of electricity. Okay, so this increased power transfer with existing transmission system. So you need not to change the system. You need not to change the existing system. What you have to do, you just introduce the new devices or new equipment in your system. Next is your availability of high power semiconductor device. Nowadays we have high power semiconductor devices, right? So from the diagram you can easily see that this is your first is your control center and control power, central power station, and next is your solar power plants, wind power plants, micro turbines, hospitals, commercial buildings, fuel cell, combined heat and power plant, factories, commercial building, house, uh, apartment and buildings. So basically, why we are using this diagram? So you can see what is the on the top of this diagram, what this is your control center. So these are the centers, these are the different sectors where you have to control the electricity or control the power. Now, how can you control the power? You can control the power on a very cheaper cost and very efficiently by using the power electronics components, right? So these are the different centers where you need to control the power. So listing of power electronics applications. So these are the different applications of power system. Distributed generation. So what is distributed generation? Distributed generation is your renewable energy sources in which wind and photovoltaic cells counts. Okay, so what happened in a photovoltaic cell? There is a solar plate which is made by power electronics components, which is your PN junctions. And PN junction, what is PN junction? PN junction is a power electronics component. These are diode. Okay. Next is your fuel cell and micro turbines. And nowadays we are using most important thing, which is your battery. So what is battery? Battery is also a power electronic device where you are the battery which is you are using in your phone, either your inverter, either at your home, where these are all power electronics components. Next is your superconducting materials, flywheels, Energy storage devices are all are constructed by power electronic components. Next is your power electronics loads, adjustable speed drives, power quality solution, dual feeder, uninterruptible power supplies, dynamic voltage restorer, transmission and distribution. So, role of power electronics in important utility applications, adjustable speed drives. So, this is a basically part of your electrical. Okay. So, you can see n number of machines in industry or at your home. We can take the example of your fan. So nowadays, how you are controlling your speed of the fan? We are using power electronic components to control the speed of fan. Okay, the regulator which you see in at your home, at your office, which is constructed by power electronic component, which is called your triac or diac. Okay, these are power electronic components by which you can control the speed of a motor. Okay, so in day to day life, n number of power electronic devices we are using. Okay, so this is your, like you can see, like utility, which is your AC supply. What happened after utility? You can see a rectifier. So what is the use of rectifier? Rectifier converts your AC to DC. Okay, it is converted into AC to DC. Then you can see a one capacitor is connected in parallel with rectifier. So what is the use of this capacitor? It is used to keep the voltage constant, no fluctuation, nothing. Okay, then switched mode converter or controller. After capacitor, a controller is converted in connected into the parallel with the capacitor, which control your voltage. And this controlling device is control your motor speed. Okay, so this is the another application of your power electronic devices. So what is the role of power electronics is important utility applications. So I have already told you that there are n number of applications of power electronic devices. If we talk about utility, then there are n number of flexible AC transmission components. Okay, you can say flexible AC transmission system, by which there are n number of fact devices. By using those fact devices, you can easily control your transmission system, and you can easily control your quality of electrical energy, and you can also reduce the cost of electrical energy. Next, this is the application of industrial applications of power electronic devices. So motor drives, electrolysis, electroplating, induction heating, welding, arc furnaces and ovens, and lighting. Next is your photovoltaic cell. So what is your photovoltaic cell? You can see in the diagram. In fact, in day-to-day life, we can see anywhere photovoltaic cells. So these are PV array. These are PV array, and this next is your solar controller and DC system. So what happened when sunlight fall on the PV array? It converts it into the DC, and DC is stored in the battery in the form of battery. Then it is fed to the inverter. So what is the use of the inverter? Actually, inverter convert DC to AC. Then it is transferred to AC bus system, and then you this AC you can use in diesel generator or AC load. So you can see the PV array is also photovoltaic cell is also a power electronics device. So these are the different kind of rectifiers, PWM rectifiers. So we will discuss it about later. These are the different kind of AC machines, inverters, and it somehow it is very useful. Hybrid cars. In these days, we are using hybrid cars, which is a hybrid car in which the primary electrical system is dominated by power electronics. Electric cars offer high performance, zero tailpipe emission, and low cost, but are still limited in range by the need of batteries. Hybrid car designs use various strategies to combine both an engine and electrical elements to gain advantages of each. Inverters and DC to DC converters rated for many kilowatts primary energy control blocks. So these are the transportation applications. You can see a number of power electronic components or devices in trains and locomotives, subways, trolley buses, magnetic levitations, electric vehicle, automotive electronic, ship power system, aircraft power system, and etc. Spaceship power system, satellite power system, space vehicle power system trend. It is estimated that in developed countries now 60% of the electrical energy goes through some kind of power electronics converters before it is finally used. So power electronics has been making major contribution to better performance of power supplies and better control of electric energy saving and environment protection. Heat removal mechanism. These are different kind of heat removal mechanism which is used by electronic components like fin type heat sink, SCR on power packets, your assembly of power converters, SCR on air cooled kits. These are the different kind of heat removal mechanism which is also constructed by power electronic devices. These are the which is very important. You must go through this slide because there are n number of power electronic devices with their rating. For example, we can take power diodes. So what is the rating of power diode? It is very high. It is very high. You can see it can work upon power diodes can work on 4000 volt and 4500 amperes, which is very high, and 1000 uh, hertz frequency. Like this, there are power transistor, thyristor, silicon control rectifier, which is very high voltage and current rating. So this is the final. We have already discussed about what is power electronics and different kind of power electronics components and what are the applications of power electronic devices. So you can refer these books to go through. You can refer these books for your power electronics components, different type of power electronic devices. These are the MCQ. So after this lecture, I expect you would be able to attempt these questions. If you have any query, you can ask. Thank you. Thank you so much.